In this video, we're going to look at points of inflection, and in particular, we're going to try to think about how can we try to identify these points of inflection. All right, so recall, a point of inflection is a spot where our function, where our graph is going to change from concave up to concave down, or it changes from being concave down to concave up, right? And so where can that happen? Well, those points of inflection, we can see those if this is an inflection point, then either the second derivative is 0 or the second derivative does not exist. So that is what would happen if it's an inflection point. Either our second derivative is 0 or it does not exist. So let's see if we can find some inflection points for this function. So to find those, we're going to take our first derivative. Our first derivative is 4x cubed minus 48x. Then we will take our second derivative. Our second derivative is 12x squared minus 48, which is 12 times x squared minus 4, which you could factor further into 12 times x plus 2 times x minus 2. What are we going to do with the second derivative? Well, we're going to see, is there anywhere where it's equal to 0? Is there anywhere where the second derivative does not exist? So let's set it equal to 0. And when we set it equal to 0, we find x equals 2 and negative 2. And so you might say, oh, so when our x value is 2, if we plug that into the original function, that will give us an inflection point. And that is almost right, but not quite. So the reason why that's not quite correct is because this is our only, so if we have an inflection point, then this will be true. One of these two things. But if one of those two things is true, it doesn't necessarily have to be an inflection point. So we should really check to see, do we actually have an inflection point, or is this not an inflection point? And so to check that, what I would do is I would create a sign chart for the second derivative. So just like we did for the first derivative, we're going to go from negative infinity up to negative 2 here. We'll go then from negative 2 to positive 2, and then 2 to infinity. We're going to think about what is the sign on that second derivative. Well, so the sign on that second derivative, if we have values between negative infinity and negative 2, we can just plug those in to one of these representations of our second derivative, plug in some value in here. So you could pick negative 3, negative 10, negative pi, negative 10 million. Just pick some value in this interval, plug it into your second derivative, and see if that is positive or negative. So if I plugged in negative 3, I like to look at the factored form. If I plug in negative 3, we have a positive 12, a positive. Negative 3 plus 2 is a negative, so we have a positive times a negative. And negative 3 minus 2 is negative, so we have a positive times a negative times a negative. If we do that, we are going to end up with a positive. So for negative 3, we have a positive value. If we plug in, say, some value between negative 2 and 2, say 0, our second derivative will be negative. And plugging in something larger than 2, we will get a positive second derivative. So we can see that our concavity of the function is going to change from concave up to concave down at negative 2. So negative 2 comma f of negative 2 is an inflection point, and 2 comma f of 2 is also an inflection point. because at 2, when our x value is 2, it changes from concave down to concave up. And so at this point, it is gluing together this change in concavity. All right, so let's find f of negative 2 and f of 2. We're going to plug those back into the original function. So negative 2 comma negative 80 and 2 comma negative 80 are both inflection points. So let's walk through that whole process. Let's look at it and think about what were the steps that we went through. So to find open intervals on which a function is concave up or concave down, we can use these following steps. So we will locate the inflection points of f along with any points of discontinuity. So don't overlook those points of discontinuity. If it's not continuous at a point, you can change concavity. So if there was a vertical asymptote, to the left of that asymptote, it could be concave up, and to the right, it could be concave down. So it can change at those points of discontinuity. It can change concavity there. You also want to determine the sign of our second derivative for at least one test value in the intervals, and then determine whether it's concave up or down on each of the intervals. So we found on that previous page that our second derivative was 12x squared minus 48, which was 12 times x plus 2, x minus 2. At 2 and negative 2, those were the places where our second derivative was 0. So when we go from negative infinity up to negative 2, and then from negative 2 to 2, and then from 2 to infinity, we do a sign chart for the second derivative. So our second derivative was positive, and then negative, and then positive. We plugged in some value between negative infinity and negative 2. So we determined that by plugging in test value. And because it's positive, that tells us then that f is concave up. Here, it's concave down in that next area, and then concave up. So it is concave up on the interval from negative infinity to negative 2, union with 2 to infinity, and it's concave down on the interval from negative 2 to 2. Excellent. Come back for our next video. We will look at another example that we will work from beginning to end. We will see you there.